Good afternoon, ladies, gentlemen, students. I don't know who's which, but I'm sure you do. In the normal course of events, I would talk about storage, because that's what I'm working on with Wyn Rampant. But Wyn has already given a very splendid inaugural lecture on storage, and reprising that for you would just be a disappointment for you, I'm sure. Daniel Friedrich has given a great presentation on storage within the last couple of weeks, and again, that's available on video. So rather than give you a storage overdose, I thought I'd talk about one of my pet gripes, which is the huge variability in costs of CO2 emission and rewards for not CO2 emission. That huge variability has some consequences which I want to talk about. Just to set the scene, a power station, I'm not sure this is actually a European power station, has to pay something like $10 for every tonne of CO2 emitted. The existing subsidies for solar PV in the UK run out at something like 340. But before I get into this, I'm going to see if I can press the button to get to the next slide. Give you a bit of outline bio. Because it may well be that some of the other things I worked on are way more interesting to you than what I'm going to talk about today. And if it turns out that you are way more interested in something else I've worked on, well, that would be great. So I kicked off, or somebody once introduced me as having started life in the Cambridge Engineering Department. Well, their biotech is good, but it's not that good. I did my engineering degree in Cambridge, and I stayed on to eventually work on a PhD called Control and Optimization of a Wave Energy Device. And I am eternally grateful to Stephen, who's sitting here, for letting me camp in his wave energy project many years ago and letting me use his excellent narrow tank. I kicked off trying to characterize hydrodynamics in a way that control engineers will understand, so I did system identification, and I got stuck into some optimal control theory in wave energy, which I then moved on to the Central Electricity Generating Board, which everybody under 30 will not have heard of, but it was the national electricity supply outfit, which also did research on wave energy and tidal at the time. So again, I did some work on optimization of tidal estuary dynamics and control engineering. I did some wide tank experiments in Edinburgh, and here's a picture up the top just to prove I used to have hair. Well, that is me, honest. And so eventually the CEGB said, well, all this wave and tidal stuff is just greenwash. We want you to be a real man and write assembly code to drive robots inside reactors. And I wasn't very buzzed by assembly code, so I went off to UCL initially as a researcher to work on tension-leg platforms. We don't have a lot of time, so I won't tell you exactly what a tension-leg platform is, but suffice to say they had some interesting dynamical issues. But the project that was as pitched was quite straightforward, so I quickly got the opportunity to turn into a lecturer and worked again on wave and tidal power, directional waves, remotely operated vehicles, system identification and control. And taught ship manoeuvring. I bet probably most of you don't know that ship manoeuvring is a mini lecture course of great detail and tedium, but I taught that for several years. I'd also got into interesting issues around subharmonic excitation on moorings. Well, eventually I tired of academia, I'm afraid, and moved on to work for Conoco, as it was at the time. They'd just put in the first real tension-leg platform, so I had a good time looking at all the real data that came back from that, correlating that with theory and trying to figure out what worked and what didn't. I worked on weight reanalysis to see how much more weight you could get onto the beast, designed a TLP for 1,000 metres in the Atlantic, which unfortunately we never did build, since there was an inadequate amount of oil in the right place. And I eventually worked on the Hadron project, and this is Hadron. It's the world's first and probably last concrete tension-leg platform. It's very big. Each of these columns is 31 metres, so you could fit a sensible sized municipal swimming pool inside each one. It weighed about 260,000 tonnes, and it had some extremely exciting and unexpected responses in the tank. And so we had quite a fun time discovering what third-order things were going on in wave crests, which were causing all of these problems. I also had fun working on the tow out of the tethers, and even more fun resolving the sinking of one of them, which was a teensy bit embarrassing when you've got a $3 billion project and lots of rather important managers whose careers rest on this thing being done. It's quite worrying when one of the tethers sinks, and I discovered how great it is to be the only person around whose fault it wasn't. I had a very nice time watching everybody else poleaxed with guilt. So after Hadron, somebody rather unimaginative said, well, you need to move to Aberdeen or else, and I quickly decided that or else would be fine, give me the money. And I unfortunately-ish ran into the guy who ran the gas group, and he wanted somebody who did numbers. He had lots of marketers who did lunch, and nobody who did numbers. So he thought he was giving up a lot of value in optionality in gas contracts, so I worked on that for a bit. I got a go at sustainable development, greenhouse gas policies, renewables, and as luck would have it, Winrampen was doing great things with hydraulics at the time, and we decided that a hydraulic transmission for a wind turbine would be something well worth investigating. And while Conoco and eventually ConocoPhillips didn't carry this through to fruition, it was the beginnings of the work that led to the MHI buyout of Artemis and the Sea Angel wind turbine, which is being put through its paces as we speak. And eventually the group that I was in, after the merger, the group that I was in metamorphosed into a technology ventures group. So my last few years have been working on evaluation of technologies, evaluation of companies and ideas for venture capital type investment. We also got involved in energy storage through Artemis again. There was some investment went into that. And working in VC type investment, you are not really an engineer and you're not really an economist. You sort of wander around in the badlands between economics and engineering, and you're not a proper one of either. You do get a bit of an interesting view from that point, and that's what I'm going to talk about subsequently. Should also mention, I suppose, this last photograph, which I haven't talked about. ConocoPhillips sponsors a prize at another Scottish university that I won't be so tasteless as to name, and that produces a prize for solutions to an environmental problem, which covers a multitude of sins. So for the last 8 or so years, I've read 300 or 400 one-page submissions and helped drill those down to about 10 decent-sized submissions for the great and the good to have a go at. This gentleman here is part of a group called Lion Guardians, who won the prize one year, and the lady who won the prize was very brilliantly managed to persuade young Maasai warriors that conserving lions was actually a better deal or a better way of acquiring prestige than killing them. So that's roughly what I've done. I'm now working on, as I say, energy storage, conceptual design and modelling, and maybe later in the year when we've made some really decent progress we'll come back and talk about it. But let's just move on now to what I'm proposing to talk through. Economics and regulation aren't necessarily very interesting to us as engineers, but they really drive what we do, and they really set the scene for everything that we tackle. Now, if you're going to spend the rest of your life designing cooling channels for turbine blades, which I must say is a very worthy enterprise, you probably won't need to know any of what I'm going to talk about. But if you're interested in setting research direction in clean tech, maybe there's something useful in this. So we don't have to be interested in these things, we do have to understand them. And understanding involves numbers, I'm afraid, so there are going to be some numbers in this discussion. Numbers and politicians don't mix very well, sometimes even numbers and regulators don't mix very well, but engineers and numbers really ought to mix. So climate change is a huge driver of policy, and CO2 is a big chunk of the whole climate change discussion. And so getting things right in CO2 pricing is, I think, fairly pivotal. Now, money and CO2 are both fungible. Now, fungible is an economist's big word, and if you haven't been brought up as an economist, you may not know what fungible means. All it says is that if something is fungible, any one unit is indistinguishable from any other unit. So if you've got an overdraft, students have overdrafts, don't they? They don't have money in the bank, but if you've got an overdraft of £505, you can't tell if the last £5 was that generous birthday present you bought your mum or what you spent on tequila shots 2 nights ago. Similarly, a tonne of CO2 emitted in Beijing, has exactly the same effect on the atmosphere as a tonne of CO2 emitted in Birmingham, say. The atmosphere is very good at moving CO2 from one place to another. So we'd expect to see one penalty for emitting CO2 and an equal reward for not emitting CO2. And many ways of reducing CO2 are also ways of creating energy. You might expect some premium or some prize for making local energy that doesn't have to be imported. So at most you'd expect one or two prices for CO2. One for not emitting CO2 and maybe another one for providing energy that's not imported. But that's not really what happens. The way our economic system has grown up and our taxation system has grown up, we have lots of subsidies, lots of taxes, we have very inconsistent prices and a huge range of prices. So it's a bit like the village fete where everybody has to get a prize. We don't absolutely have everybody getting a prize. Nobody has a subsidy yet for hamsters that run around in little wheels and make electricity. And yes, they create lots of jobs and eat lots of barley, and that would be a great thing, but nobody's been quite that daft. But nonetheless, we do have some very expensive ways of combating climate change, which is not a good thing. One of the problems is that if you have very expensive routes, all the people who are disinclined to do anything about it will be much more strongly founded in their opposition. If combating climate change costs nothing, nobody would be opposed to it. Because some people see very large costs, they're very loath to get going on the subject. So we also need to address climate change efficiently, both to maximise results and also to free up money to address other problems. It's a huge problem in my mind, and it's a huge problem in the minds of many other people, but it's not the only problem. If you're some poor refugee and you're looking for food to eat, you will not be very pleased if you're told that all the corn has been turned into bioethanol to combat climate change, and no, you can't have anything for your kids today. So there are lots of other problems in the world other than climate change. If you can solve two at once, then good news, but whatever we do to solve climate change, we have to be responsible in the way we spend the money and get the most value for it, I think. So I'm going to talk a little bit about the misallocation. I'm going to talk a little bit about what might happen in an ideal world, which is obviously a world run by engineers. Clearly we're not going to get there. And talk a little bit also about implications for storage, if I have time. So most of us are not very well calibrated in what $100 a tonne of CO2, say, would mean. I'm using $100 because it's a nice round number. If you know the numbers for 100, then you can scale up or down. But as far as the user is concerned, $100 a tonne on CO2 just means more expensive energy. So how much more expensive? Let's start with coal. The market price of coal is $30 to $80 a tonne. Might be 20 if you're in the Powder River Basin in Wyoming, right at the mine mouth, but by the time you've put a tonne of coal on a railroad and moved it 2,000 miles and stuck it on a boat, taken it to Rotterdam, it'll probably cost you 80. But you put $100 a tonne on, and if it's average coal, coal's very variable stuff, it's not fungible. Anthracite is nearly 100% carbon. Lignite is dirt that burns. There's a big range of carbon contents, but if you had fairly average coal, you'll be looking at a penalty to burn that coal of $300 a tonne. So you're looking at something like 4 to 10 times multiplier by introducing a $100 a tonne CO2 price. So $100 a tonne is enough to blow the coal industry out of the water. Let's look at oil. Well, oil is already very expensive energy. Coal is cheap energy, oil is expensive energy. $100 a tonne on CO2 is worth $41 a barrel. Oil sold in barrels, not tonnes. And those of you who've kept track of the recent gyrations in the oil price will know that oil has fallen by of the order of $40 a tonne. So that says that the kind gentlemen who run OPEC have previously been imposing a $100 per tonne CO2 tax on oil, and of course they've been kindly keeping the money, which has been very good for them. And they've recently relaxed that. We've effectively seen a $100 per tonne of CO2 reduction in the oil price. And to my mind, that is not great for the fight against climate change. So oil typically runs $50 to $100 a barrel. $40 a tonne is a big change, but it's within the normal gyrations of the price. Gas is somewhere in the middle. Gas is less than $3 a gigajoule in the US. It's more than $6 a gigajoule in Europe. $100 a tonne will give you $5 a gigajoule change in the price of gas. So that's big, but it's not totally out of order. Looking at the effect on power, coal-fired power typically sells for $50 to $80. And by the way, apologies for the dollars, but I'm calibrated in dollars. You don't need to worry about these numbers in absolute terms. It's just the relatives that's important. The fuel cost of coal-fired power might be $25 a megawatt hour. You sell it for $50 to $80, you're in Fat City. But $100 a tonne CO2 price adds another $90 a megawatt hour to the coal-fired power price. So again, if you're a coal-fired generator, you're in bad shape with $100 a tonne. Gas is different. Gas is a bit expensive, but the fuel cost of natural gas-fired power might be $55 a megawatt hour for something that's selling 50 to 80. You'd only be adding another $38 a megawatt hour if you introduce this big price. So gas power would do very well, coal power would not. And I spent, as you know, I spent quite a long time in an oil and gas company. And one of my points was that actually a CO2 price wouldn't be very bad for an oil company because it's within the range of possibilities. It would be very bad for coal and hence great for the gas business. Unfortunately, that hasn't happened, but nonetheless, you will find that the more sophisticated CEOs of oil and gas companies are calling for a CO2 price. The guy who runs Shell has just done so within the last couple of days. So let's look now at the pivotal issue, the effective CO2 price there is out there. Now, we've said $100 would be huge for coal. It would be a bit of a big deal for oil, but not a disaster. So the EU emissions trading scheme, you can buy CO2 credits at $10 a tonne. But some of these are of dubious provenance. They come from bogus schemes in Russia to destroy HCFCs and other strange things. But dubious provenance or not, they're going to be used to emit CO2. And so they are real important CO2 credits. So if you're running a coal-fired power station, you can buy emissions rights for $10 a tonne. On the other hand, if you put PV on your roof, and the subsidy system is changing, I know, but this is the old numbers. If you put PV on your roof, solar panels, you will get a subsidy of 13 pence a kilowatt hour. And that kilowatt hour is displacing about 0.6 of a kilogram of CO2 if you're looking at average UK electricity emissions. It's displacing less if you're displacing gas-fired power, more if you're displacing coal-fired power. But using the average number, that says that you're being paid $340 for every tonne of CO2 avoided. You also get something called net metering. You can sell electricity back to the grid, whether they want it or not, at the price that you're allowed to buy it at. That's another subsidy, effectively. I've left it out because people don't necessarily get the idea immediately. But in fact, PV is effectively probably getting something over $500 per tonne of CO2 avoided. Offshore wind is a bit more cost effective. It runs out around 260 if it's getting £100 a megawatt hour. That's about what it gets. Onshore wind is even more cost effective. It looks like about $100 a tonne. And then if we look at some of the taxes on power and gas, domestic gas sees 5% VAT and another 15% of that price goes to support renewables. So we're seeing something like $50 a tonne on domestic electricity. Domestic gas we're only seeing 13. Again, back in the olden days, in Roman times before the railway came, the Conservative government lost a general election quite possibly on the basis of high retail gas and power VAT. There was a proposal to make VAT 20% on gas and power, which it is in lots of the rest of the EU, but politicians have ever since run scared. I have only to read the newspapers to see how inflamed people become about high retail prices. And so high VAT on domestic is poison. It will be a very brave politician who raises it. Nonetheless, domestic gas really is getting a pretty free ride. Now, I work for an oil and gas company. You wouldn't expect me to get off this slide without also talking about the taxation of gasoline. UK petrol tax, when you do the numbers, is about 76 pence a litre. When I put this together, the price of petrol wholesale on NYMEX exchange was about 22 pence a litre. So the tax rate on petrol in the UK is about 300%. I'm not saying that to make you feel sorry for oil companies, but I'm flagging up the fact that not everywhere has crazy subsidies for fossil fuels, and just a few places do tax them sensibly, and I think this is probably pretty sensible. So again, if I'm driving my car, I'm effectively paying $500 per tonne of CO2 emitted. If I take account of the fact that exploration and production of oil uses energy and creates emissions, and that refining creates emissions, that brings it down to about 370. Now, none of these numbers are individually important. What I'm trying to get across, though, is that there is an enormous variance between the lowest and the highest. We don't individually, because we're not economists, we don't know what the right number is, but we can be pretty clear that some of these things are too high. If I'm driving my car, I'm driving a machine that has been designed by all those clever chaps at British Motor Works who are doing what is the optimal thing in a $370 per tonne of CO2 world. And if I'm thinking of replacing my boiler, I'm only incentivised as if I was in a $13 per tonne of CO2 world. So I've said, highlighted this fact, if we have the wrong prices, then we allocate effort to the wrong problems. And it makes combating climate change more expensive than it needs to be, or we get less result than we ought to do. It creates opposition and we don't achieve enough. I think a banner example of this is the German PV disaster. Now, lots of people who haven't done the numbers think that German PV is fantastic and brilliant and wonderful. Germany has over 35 gigawatts of installed PV, and the average cost is probably $4 per watt. I'm going to use 3 just to avoid controversy. So Germany has spent $105 billion on installing PV panels. In Germany, the capacity factor is about 10%. That is, PV runs at about an average of 10% of the peak. So you would get 3.5 gigawatts average of power out of these 35 gigawatts. You could make 3.5 gigawatts with 4 gigawatts of combined cycle gas turbines, which would have cost you about $4 billion. And that would leave you a handy-dandy $101 billion over to pay for gas, because obviously you would have to pay for the gas, and that's about $2 billion a year for that amount of kit. And all the rest of it you could spend on energy efficiency, which might have freed up the gas in the first place. You could spend it on storage R&D, which I think would be a very good thing. You could spend it on carbon capture and storage. You could do a great number of things with that spare $101 billion. Now, the German programme did finance a huge build-out of capacity, and that has pushed prices down. But that capacity may turn out to be redundant if new technologies such as perovskites, which are inherently probably cheaper than silicon, if those new technologies do succeed. So what I think we ought to be able to do is trade between emissions and efficiency and renewables. And my God, I'm going slowly. And so that would allow us to cut deployment of the most expensive technologies and spend the same money on a much bigger volume of the more effective ones. And I'm going to have a quick aside on trading, because this is something that took me a very long time to get. You may think it's totally obvious and jeer and boo, but I'm going to say it anyway. Resources aren't fungible. If you want to turn gas into oil, or you want to turn sunshine into petrol, you have to work pretty hard. There's no trading allowed, or trading directly. Trading is not immediately achievable. So trading is all about finding a counterparty who has what you want and wants what you have. A great example of this is the Shell's gas to liquids plant in Qatar. Depending on who you believe, it costs between $19 and $26 billion. Gas in Qatar probably costs $1 to $2 a gigajoule because this 19 to 26 billion actually included the cost of developing gas fields and so on. So $1 to $2 per gigajoule probably pays for the gas field. Diesel used to be $16 a gigajoule. That looks like a fantastic deal. You've got something worth 1, you turn it into something worth 16. Okay, the efficiency is only 55%, so you actually need 2 gigajoules of gas to make a gigajoule of diesel. It still sounds fantastic. You've got 250,000 barrels a day input to make this 250,000 barrels a day equivalent of energy input. All that sounds great. You have to build something the size of East Kilbride, but much more expensive to make it all work. But nonetheless, it sounds a good deal. Shell did it. But right next door to Qatar, if you look at your atlas, is a big country called Saudi Arabia. They're burning 900,000 barrels a day of oil to make electricity. Well, wouldn't it be a much neater deal to take the 250,000 barrels a day of gas, sell that to them, or give it to them, and take the 250,000 barrels a day of oil? That trade is exactly the same as building that huge plant. It's a lot cheaper, and of course, if politics hadn't got in the way, it would probably have happened. But it's a huge amount of capital that's just gone down the drain, achieving precisely nothing. Let's look at biofuels. Solar to corn to ethanol is about 1/4% efficient when you look at how much sunshine falls on the field and how much ethanol you get out of it. And that excludes any fuel and power inputs that you actually needed to make the corn into the ethanol. But at the same time, we've got lots of people burning heating oil for low-grade heat, for bathwater effectively. So couldn't we just burn the corn and make the heat and take the heating oil? Again, it's the same deal. You can get 100% efficiency if you just burn the corn and displace the distillate. And of course, smart chaps like you will realise that wood is even cheaper than corn. So there's a very good trade to be done there until you run out of people who are burning oil for heat. So the lesson is unwinding an inefficiency is unusually rewarding. So in a uniform CO2 price world, it's pretty clear what we do. We wouldn't cut fuel taxes. I'm not doing a sub-story for oil companies. But we do all the profitable stuff first. You've probably all seen this McKinsey plot, which shows there's lots and lots of things that cut CO2 emissions at a negative cost. So do all the profitable stuff first, which would free up lots of money to do all the less profitable stuff. We'd stop wasting electricity and LPG and gas and oil on low-grade heat. All of those high-grade sources of energy are, they should be spent on doing high-grade things like driving vehicles or something where they're uniquely capable. So we should be focusing on insulation and biomass and heat pumps to get rid of these high-grade fuels and low-grade heat. But of course, then we'd have lots of gas to displace coal, and off we go. We'd obviously still be deploying renewables that are consistent with the carbon price. We'd be hiking energy R&D. Dieter Helm at Oxford reckon that you could probably double UK energy R&D by just making a 1% cut in the rate of deployment of solar and offshore wind. I haven't seen his numbers, but that's sounds to be about the right sort of number. We'd cut the cost of PV, or we do R&D to work on to cut the cost of PV and wind, and develop carbon capture and storage, and maybe new nuclear to eat up all the nuclear waste that we've got that we don't know what to do with. And of course, we'll be working on grid flexibility and energy storage. So I'm going to talk very briefly about grid flexibility. We need it for renewables, CCS and nuclear, because we have lots of non-dispatchable users, people who want to turn their hairdryers on. Not that that's something I do very often, but some of the rest of you do. So energy storage and flexible demand also compete with flexible generation. We've got three sources of grid flexibility. Flexible generation, open cycle gas turbines is what we've got today. But energy storage and flexible demand are all in the hopper. And I don't think energy storage is going to get a walled garden where it doesn't have to compete the way renewables didn't have to compete with conventional energy or even with each other or with energy efficiency. So we're looking at pumped heat. Obviously there are these other options, hydro, batteries, compressed air. This dispatchable demand today is probably comprises refrigeration, dispatchable heating that can be switched on and off. In the future, we might see big oxy-fuel carbon capture and storage schemes, which could be dispatchable and provide a lot of flexibility. Electric vehicle charging, more heat pumps, all of those could provide flexibility. So those of us who are working energy storage have to be very aware that we've got competition. To my mind, the big issue for the UK is what I call the 10-year anticyclone. Every 10 years, we get 2 or 3 weeks in the middle of winter where it's dark, it's cold, it's still, there's no sun, there's no wind, and there's lots of demand, and so what are you going to do about it on the energy storage front? 4 hours of batteries isn't going to get you through 2 weeks. 20 hours of compressed air energy storage isn't going to get you through 2 weeks. Something is going to have to solve the problem, and when you've got that something, what's that something going to do for the energy storage business the rest of the time? Because the rest of the time, that kit is still going to be there, it's still going to be usable, and it's going to compete with any other energy storage system you come up with. So, quick conclusions. Getting prices and incentives right is important. This is all motherhood and apple pie, I'm afraid. Incentives are probably going to get more sensible. That means when you're picking your research areas, you should be like Wayne Gretzky, the great ice hockey player. He said he skates towards where the puck is going to be. Everybody else skates towards the puck. But if you skate towards where the puck is going to be, then you have a slightly better chance of success. So we shouldn't deploy lots of suboptimal technology, but we do have to deploy some, otherwise we never learn. It's a tough balance. Germany's gone too far on the PV front probably. Other technologies we may not have done enough. And the last thing to remember is that every industry promotes itself, so do your own numbers. Okay, sorry I've gone on. That's it.
This production is brought to you by the University of Edinburgh.